Today, we will talk about the heading indicator, also known as the directional gyro. This is one of the basic flight instruments that we will find in any aircraft, and its operation is based on the gyroscopic principles. As mentioned in the video about the gyroscopic system, most of the light aircraft have the following configuration. The vacuum pump provides suction to drive the gyros of the attitude indicator and the heading indicator, while the gyro of the turn coordinator is driven by direct current from the aircraft electrical system. With this in mind, let's take a closer look at the heading indicator. This instrument is also known as the directional gyro, and it indicates the current heading of the aircraft in degrees in relation to a directional reference. Usually, the directional reference used in aviation is the magnetic north pole. However, there is a little problem with this. And it is that the heading indicator has no mechanism that allows it to determine the direction of the magnetic north. Therefore, the pilot must tell it where magnetic north is for the instrument to use it as a reference. To do this, the pilot uses the magnetic compass, since it does have the ability to align itself with magnetic north. Then, the pilot must align the heading indicator using the magnetic compass indication. At this point we might think, if we need to constantly align the heading indicator with the compass, why not use the magnetic compass alone? Well, the answer is that as we've seen in previous videos, the compass indication suffers from significant errors during turns, accelerations, maneuvers, or turbulence. And apart from this, its design causes the compass card to move in the opposite direction to the turn, making it difficult to read, especially under high workloads. On the other hand, the heading indicator does not present these errors and is much more accurate, consistent, and easier to read. That's why it is the main instrument used for heading indication. With this being said, let's see the parts of the heading indicator. First, we have a compass rose in the background. Then we have a miniature aircraft in the middle, which will represent the orientation of the real aircraft. The line that extends in front of the aircraft represents the current heading. And finally, in the lower left corner we have a cage and adjustment knob. Let's now take a closer look at the compass rose. A compass rose is basically a graphic representation of the 360 degrees of azimuth, which is printed on the instrument card. Normally, the long lines represent increments of 10 degrees, and the short ones represent increments of 5 degrees. Apart from this, the main cardinal directions are represented by their corresponding letters. For example, the letter N, which represents north, corresponds to heading 360. The letter E, which means east, represents heading 090. The letter S represents heading 180, and the letter W represents heading 270. In the same way, every 30 degrees, a number representing that heading is included, omitting the last digit. For example, the number 3 represents heading 030. The number 15 represents heading 150. The number 30 represents heading 300, and so on. Now, some heading indicators also include relative heading markings. These are reference angles relative to the aircraft's current heading. In other words, the current heading of the aircraft is used as reference, so it will represent 0 degrees relative. Here we can find the markings for 45, 90, 135, 180, 225, 270 and 315 degrees relative. And again, these angles are not measured in relation to magnetic north, but in relation to the current heading of the aircraft. We will see later with some examples how they are used. Now, to finish with the parts of this instrument, some heading indicators also incorporate a heading bug and its corresponding heading knob. This allows the pilot to select a particular heading in the instrument. It is often used as a reference during manual flight, but can also be used in conjunction with the autopilot system. Having seen all this, let's see how to read this instrument properly. Here, as we can see, the line that represents the current heading is on the north marking, which means that the current heading is 0 degrees. If the aircraft now turns to the right in such a way that we have now this indication, we would be flying with heading 060. Now, if the aircraft turns to the left this way, the heading is now 320. In this other situation the heading would be 090. And here the heading is now 285. As we could see, the heading indicator is quite intuitive and easy to read. Let's now see how to use the relative heading markings. Let's say that with this current heading of 285, the ATC tells us to make a 45-degree turn to the right. He is not asking us to turn to heading 045, but to turn 45 degrees to the right in relation to our current heading. Clearly we could add 45 degrees to heading 285 to determine the heading to which we must turn. But it is easier to use the relative heading markings of the instrument. In this case, we just have to look at the 45 degrees relative marking, which indicates heading 330. So we just have to turn to that heading. Now, let's say that the ATC asks us to make a 90-degree turn to the left. In this case, we just have to look at the corresponding relative marking, which in this case indicates heading 240. So we just have to turn to that heading. Having seen how to use this instrument, let's see how it actually works. As we already mentioned, the heading indicator uses the gyroscopic effect of rigidity in space. Specifically, this instrument incorporates a horizontal gyro so that the plane of rotation is perpendicular to the horizon. This gyro has 3 degrees of freedom, which means that it can rotate freely around all 3 axes. This implies that, once aligned with the reference heading, the gyro will remain rigid in space, regardless of aircraft movements, making it an excellent reference to measure the heading. Let's see how this instrument works in practice. On the right side we have the instrument as the pilot would see it. And on the left side we are looking at the instrument from above. In this case, it is indicating a north heading. If the aircraft makes a turn to the right, both the aircraft and the instrument will turn to the right, while the gyro remains rigid in space. This way, the instrument can measure the angle between the directional reference and the current aircraft heading. And the same happens if the aircraft turns to the left. In this case both the aircraft and the instrument will turn to the left, while the gyro remains rigid in space, allowing to measure the heading correctly. Now, as with other instruments, the heading indicator is not perfect, and therefore it has certain limitations. And it is that, although theoretically the instrument's gyro has 3 degrees of freedom, in reality it has mechanical stops that prevent the gyro from rotating completely freely. This implies that upon reaching excessive pitch or bank angles, the mechanical stops will prevent the gyro from rotating freely, causing the instrument to topple and become inoperative until it is reset by means of the adjustment knob. Typically on electric-driven heading indicators, the pitch and bank limits are around 85 degrees. While on the other hand, on air-driven gyros, the limits are more restrictive, around 55 degrees. Now, this is not the only limitation of the instrument, since it also suffers from gyroscopic apparent wander. Let's see what is this. As we know, when the gyro starts spinning, it remains rigid in space. However, the Earth does not remain static, it rotates at about 15 degrees per hour. To understand how this affects the gyro, here we have the Earth seen from above. Let's suppose we are at this yellow point, and we align the gyro of the heading indicator in such a way that it points to the north. Now, after a few hours, the Earth would have rotated several degrees, so let's say that we are now at this other position. As we can see, as the gyro remains rigid in space, it is no longer pointing to the north, and it has now a deviation of 60 degrees. This implies that the heading indicator will be using a wrong directional reference, so the heading indication will be incorrect. This apparent wander error can be up to 15 degrees per hour near the poles. And it is that the apparent wander is maximum at the poles and minimum at the equator, but let's see why. In the image on the left we can see that near the poles the apparent wander is significant. However, in this image on the right we can see that at the equator, the plane of rotation of the gyroscope remains aligned with the meridians pointing north, regardless of the rotation of the Earth, so then we say that there is no apparent wander at the equator. Based on this, we can deduce that the magnitude of the apparent wander depends on the latitude and can be determined by means of this formula. Now, this wander is known as apparent, since in reality it is not the gyroscope that drifts, but the rotation of the Earth that creates this effect. Now, there is another effect known as real wander. And it is produced since the mechanisms and gears inside the instrument are not perfect, they suffer from wear, friction, and imbalance. That causes the plane of rotation of the gyro to drift due to precession. However, this error is normally small. In well-maintained modern gyros, the real wander is very low, around 1 degree per hour. Taking into account the effects of real and apparent wander, the question is, how do we correct the instrument indication? Well, for that we have to use the cage and adjustment knob. This allows the gyro to be disengaged from the card. This makes the gyro act as a free gyro and does not topple with excessive maneuvers or attitudes, as well as allowing the card to be realigned with the magnetic compass indication. As a general rule, to avoid significant indication errors, the pilot should realign the heading indicator with the compass every 10 to 15 minutes during flight. However, this adjustment should only be made when flying straight and level, with a constant speed, as this is the only situation in which the compass will indicate the heading correctly. Let's see an example of how to reset the heading indicator with the compass. Let's say we are flying straight and level, with a heading of 120. In this case, both the compass and the heading indicator are indicating the same heading. However, due to the effects of real and apparent wander, the heading indicator will drift progressively with time. In this case, now the heading indicator is showing a heading of 110, even though the compass continues to indicate the correct heading of 120. In this situation, the pilot will have to use the adjustment knob to reset the heading indicator according to the magnetic compass indication. But again, this should only be made while flying straight and at a constant speed. Now, up to this point we have seen how a conventional heading indicator works. However, there is a variant of this instrument, known as the gyromagnetic compass, which is also known as the remote indicating compass or the slave gyro compass. Basically, it consists of a heading indicator that instead of incorporating a free gyro, has a slave gyro. It uses a system of remote magnetometers to determine the direction of magnetic north, and this way it automatically and constantly realigns the instrument's slave gyro with magnetic north. But we will deal with this instrument in detail in another video. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below. Thanks for watching.